What if everything we thought about the origins of life was wrong? What if Earth wasn't the cradle of life, but Mars was? Billions of years ago, the red planet had rivers, lakes, and even oceans. Could we and all life on Earth be the descendants of Martian microbes? Today, we dive deep into one of the most fascinating questions in science. Did life begin on Mars before it ever reached Earth? Investigating life on Mars. For generations, scientists have sought to unravel the mysteries of life's beginnings. How did inanimate molecules organize themselves into the intricate, self-replicating systems we know as living organisms? And why did this extraordinary phenomenon occur on Earth? Yet, as we uncover more about Mars's ancient history, tantalizing clues suggest it may have been a more promising environment for life billions of years ago than our own planet. Mars cooled faster, its surface likely harbored water earlier, and its chemical composition may have been particularly suited for jump-starting biological processes. What if, rather than being Earth's lesser twin, Mars was the elder sibling that sparked life in the solar system, only for that life to later migrate here? One must first examine the conditions of the early solar system. Billions of years ago, our young solar system was a chaotic, violent place. Planets were still forming, colliding with debris left over from the solar nebula. Among this celestial tumult, Mars stood out. Unlike Earth, which was still in the throes of its molten infancy, Mars cooled and stabilized relatively quickly. This rapid cooling allowed liquid water to flow on its surface, an essential ingredient for life as we understand it, potentially creating a hospitable environment long before Earth's surface became temperate. The early Martian atmosphere was likely denser than it is today, creating a greenhouse effect that warmed the planet and allowed water to persist in lakes, rivers, and perhaps even shallow seas. Geological evidence gathered by missions like NASA's Perseverance and Curiosity rovers shows ancient riverbeds, deltas, and sedimentary layers that tell a story of a wetter, more temperate Mars billions of years ago. If these conditions existed, they could have supported the chemistry needed for life to emerge. Mars's ancient landscapes, now barren and desolate, may once have been cradles of life, nurturing primitive microorganisms in their primordial waters. Mars's chemical composition further strengthens the case for its habitability. Unlike Earth, where geological activity constantly recycles materials, Mars's surface preserves its ancient chemical history, offering a snapshot of the planet as it was billions of years ago. Among the most compelling discoveries are the presence of phosphorus and boron, critical elements for the formation of RNA, one of life's fundamental building blocks. These elements, found in Martian meteorites and analyzed by rovers, suggest that Mars may have had the raw materials needed to catalyze the origins of life. Moreover, the abundance of iron, sulfur, and silica on Mars creates an environment ripe for prebiotic chemistry. Laboratory experiments on Earth show that such minerals can facilitate the assembly of complex organic molecules. On Mars, these processes could have been accelerated by volcanic activity and the interaction of water with the planet's mineral-rich crust. In addition, the discovery of organic molecules by the Curiosity rover hints that Mars was once a chemically dynamic environment, capable of sustaining the complex reactions required for life to emerge. But even if life did originate on Mars, how could it have traveled to Earth? This question leads us to the intriguing concept of panspermia, the idea that life, or its precursors, can be transported between planets via meteoroids. In the solar system's early years, massive impacts on Mars would have ejected rocks into space, some of which eventually landed on Earth as meteorites. Today, we have identified dozens of Martian meteorites on Earth containing trapped gases identical to those in Mars's atmosphere. Could these meteorites have carried with them the seeds of life, or at least the building blocks necessary to kickstart it on Earth? This hypothesis gains credibility when considering the resilience of microbial life. On Earth, extremophiles, organisms capable of surviving in the harshest environments, thrive in conditions once thought impossible. Experiments have shown that certain microbes can endure the vacuum of space intense radiation, and extreme temperatures. If life began on Mars, it is conceivable that primitive microorganisms could have survived the interplanetary journey embedded in rock, arriving on Earth to find a hospitable new home. Proposing that life began on Mars before Earth challenges deeply ingrained assumptions about our planet's uniqueness. For centuries, Earth has been seen as the focal point of life in the cosmos, a special singular world in a universe of lifeless orbs. But what if Earth's biosphere owes its origins to Mars? What if life is not an Earth-centric phenomenon, but a cosmic inevitability, arising wherever conditions permit? This paradigm shift would have profound implications for our understanding of life's place in the universe. Skeptics argue that the evidence for Martian life remains circumstantial, and that Earth's more dynamic geological and atmospheric systems make it the more likely cradle of life. However, this perspective does not preclude the possibility that Mars played a role. The interplay between Mars and Earth in the solar system's early years was likely far more interconnected than we once believed, with the two planets exchanging materials and perhaps even life across eons. As we continue to explore Mars, the search for definitive proof of past or present life takes center stage. Missions like Perseverance are equipped to analyze rock samples in unprecedented detail, seeking biosignatures, chemical markers that could indicate biological processes. Future missions, including the highly anticipated Mars Sample Return, aim to bring Martian rocks back to Earth for analysis in state-of-the-art laboratories. These efforts represent humanity's most ambitious attempt yet to answer one of the greatest questions of all time. Are we the cosmic descendants of a Martian ancestor? If life is found on Mars, even in its simplest microbial form, it would revolutionize our understanding of biology and planetary science. The discovery would confirm that life can arise independently in multiple locations, strengthening the case for its existence elsewhere in the universe. But then, how would life have started on Mars? Early solar system dynamics. The story of life as we know it begins in the chaos of the early solar system, a time when our sun was just a fledgling star surrounded by a swirling nebula of gas and dust. From this cosmic nursery, the planets emerged, forged in the crucible of collisions, chaos, and unimaginable heat. It was a violent epoch, but also one filled with potential, a time when the building blocks of life were scattered across the nascent solar system, waiting to seed worlds like Earth and Mars. But what if Mars, not Earth, was the first planet to grasp this potential? What if, in those primordial times, the red planet experienced its own flourishing age of habitability, hosting the earliest sparks of life? 4.5 billion years ago, the Sun was born from the gravitational collapse of a massive cloud of gas and dust. As the Sun ignited at its core, the surrounding material flattened into a protoplanetary disk. Within this disk, tiny grains collided and stuck together, growing into pebbles, then boulders, and eventually planetesimals, the building blocks of planets. These planetesimals collided with one another, their immense energy melting their surfaces and allowing heavier elements like iron to sink to their cores. Over millions of years, these repeated impacts gave rise to the rocky planets, including Earth and Mars. This was not a peaceful process. The young solar system was a chaotic dance of collisions, with planetesimals smashing into forming planets and each other. Some were obliterated, while others grew larger with every impact. It was in this violent crucible that the unique trajectories of Earth and Mars were set, defining their paths for billions of years to come. Despite their shared origins, Mars and Earth embarked on very different developmental timelines. One of the most critical factors in this divergence was size. Mars, being only about half the diameter of Earth, cooled far more quickly. While Earth's larger mass retained its heat, keeping its surface molten for millions of years longer, Mars rapidly developed a stable crust. This stability allowed the formation of liquid water on its surface far earlier than on Earth. The smaller size of Mars also meant that its volcanic activity subsided sooner, and its weaker gravity struggled to retain a thick atmosphere. In contrast, Earth's ongoing volcanism released vast quantities of gases that formed a dense protective atmosphere, but it took much longer for conditions to stabilize enough for life to emerge. For Mars, this early cooling presented a unique opportunity, what some scientists call its ancient habitability window. Billions of years ago, Mars was a world of rivers, lakes, and possibly even oceans. Its surface was warmer and wetter than the cold, arid desert we see today. Evidence of this ancient climate is etched across its surface in the form of dried riverbeds, sedimentary layers, and delta formations. While Earth was still a molten inferno, Mars may have been hosting stable bodies of liquid water, a critical ingredient for life. During this period, the red planet's atmosphere, though thin by Earth standards, likely provided sufficient warmth for liquid water to persist. Coupled with the heat generated by volcanic activity and the presence of essential elements like carbon, hydrogen, nitrogen, and phosphorus, Mars had all the ingredients needed for prebiotic chemistry. If life began anywhere in the solar system, this early Mars, teeming with potential, was an ideal candidate. The story of life's emergence on Mars, and later on Earth, cannot be told without understanding the role of asteroids and comets. These celestial messengers bombarded the inner planets during the solar system's infancy, delivering water, organic molecules, and other life-building materials. It's believed that these impacts played a critical role in shaping the environments of both Mars and Earth. Mars, with its proximity to the asteroid belt, may have received a different mix of materials than Earth. The impacts themselves created temporary habitats, with hydrothermal systems forming at impact sites. These hot, water-rich environments could have provided the perfect conditions for the synthesis of complex organic molecules, perhaps even the first primitive life forms. Earth, meanwhile, was not so fortunate during its earliest days. The sheer intensity of asteroid impacts likely vaporized any nascent oceans and sterilized the planet's surface multiple times. While Mars was enjoying a period of relative calm and stability, Earth was locked in a cycle of destruction and recovery, delaying the onset of habitable conditions. Around 4 billion years ago, the solar system experienced a cataclysmic event known as the Late Heavy Bombardment, LHB. This period, characterized by an intense barrage of asteroids and comets, reshaped the surfaces of the inner planets. For Earth, the LHB may have been both a curse and a blessing. On one hand, the impacts likely delayed the emergence of stable environments by sterilizing large portions of the planet. On the other hand, the influx of water and organic materials provided by these celestial impacts laid the groundwork for future habitability. Mars, with its smaller size and thinner atmosphere, may have experienced the LHB differently. While its surface was also pockmarked with craters, the relative lack of tectonic activity on Mars meant that many of these ancient scars remain visible today, offering scientists a window into this turbulent period. Could it be that the LHB, while destructive, provided Mars with the final push it needed to transition from a merely habitable world to a potentially inhabited one? The dynamic forces of the early solar system raise an intriguing question. If life began on Mars during its ancient habitability window, could it have been transported to Earth via meteorites? Scientists have identified Martian meteorites on Earth, ejected from the red planet by asteroid impacts and later falling to our planet's surface. If microbial life existed on Mars during this time, it's conceivable that these spacefaring rocks carried living organisms, or at least the precursors of life, to Earth. This idea, known as Panspermia, suggests a shared origin for life on Earth and Mars. In this scenario, Mars acted as the cradle of life, with Earth eventually inheriting the legacy of its neighbor. While this remains a theory, ongoing studies of Martian meteorites continue to search for traces of ancient life or organic materials that could support this remarkable possibility. Today, Mars is a shadow of its former self. Its ancient lakes and rivers have long since dried up, its atmosphere stripped away by solar winds. Yet, the evidence of its habitable past endures, waiting to be uncovered by robotic explorers and, perhaps one day, human missions. The story of early solar system dynamics reminds us that Mars was not always the barren world we see today. It was once a world of possibility, a silent witness to the birth of life, or perhaps its earliest host. Mars, an ancient oasis. Mars has long captured the imagination of humanity, not just as a neighboring planet, but as a world that might once have been alive. Billions of years ago, the red planet wasn't the dry, barren landscape we see today. Instead, evidence suggests it was a world rich with water, harboring rivers, lakes, and possibly even oceans. These features, coupled with a climate that might have been far more hospitable, make Mars one of the most compelling candidates for understanding the conditions necessary for life. Mars wasn't always the dusty desert we know today. Its ancient landscape tells a very different story, one of flowing water and dynamic geological processes. River valleys snake across the Martian terrain, carved out by liquid water billions of years ago. These networks of dried-up riverbeds suggest that surface water once flowed consistently, possibly over millions of years. Craters like Gale and Jezero show clear evidence of deltas, sedimentary formations created by rivers emptying into lakes. These features indicate a time when water pooled in great basins, forming lakes that could have supported life. Layered sedimentary deposits in these regions point to slow-moving waters, shaping Mars's surface and creating habitats that may have been ideal for microbes. Other geological features reinforce the narrative of Mars as a watery world. Alluvial fans, formed by debris washed down by water, hint at episodic flooding events that transported materials across the planet's surface. Even impact craters, scarred reminders of violent collisions, show erosion patterns consistent with flowing water. In more recent observations, scientists have detected recurring slope lineae, dark streaks on Martian slopes that may represent seasonal water flows or brine seeping to the surface. Together, these features paint a vivid picture of ancient Mars as a world where water wasn't just present but abundant. To sustain such an environment, Mars would have needed a climate far different from its current freezing, desiccated state. Billions of years ago, Mars was warmer and wetter, conditions that would have allowed liquid water to persist on its surface. At that time, the young sun was less luminous, but Mars's position near the snow line, a region in the solar system where water ice is stable, meant it could take advantage of modest warming from greenhouse gases. Geological evidence suggests that volcanic activity on Mars released significant amounts of carbon dioxide and water vapor into the atmosphere, creating a greenhouse effect that trapped heat and kept the surface temperatures above freezing. Climate models of ancient Mars also point to cycles of rainfall or snowmelt, which would have further shaped its terrain. These wetter conditions likely fluctuated, with periods of aridity followed by episodes of abundant water. Volcanic eruptions, releasing ash and gas into the atmosphere, might have periodically warmed the planet, melting ice and jump-starting water flow. Mars's atmosphere, far thicker than it is today, would have played a crucial role in regulating these processes. The thicker atmosphere that once enveloped Mars was a cornerstone of its ability to support liquid water. Today, Mars's atmosphere is a thin, fragile shell, but billions of years ago, it was dense enough to maintain surface pressure conducive to liquid water. Studies of Martian meteorites and surface isotopes suggest the planet had a nitrogen-rich atmosphere with traces of argon and other gases. This atmospheric density would have not only supported liquid water, but also shielded the surface from harmful cosmic radiation, creating an environment that could sustain life. Over time, the planet's magnetic field, which protected its atmosphere from the solar wind, weakened and eventually disappeared. Without this shield, solar winds stripped away the atmosphere, thinning it to the tenuous state we see today. This loss of atmosphere likely marked the end of Mars's ability to support liquid water on its surface, driving the planet into its current arid state. But before this atmospheric decline, Mars may have boasted features that rivaled Earth's oceans. Scientists hypothesized that vast oceans once covered the planet's northern hemisphere. These ancient Martian seas might have contained enough water to cover the entire planet to a depth of hundreds of meters. Shorelines, identified through topographic mapping, suggest the northern lowlands could have been a giant ocean basin. Sedimentary deposits along these shorelines point to persistent bodies of water that existed for millions of years, creating environments potentially teeming with life. Even as Mars transitioned to a colder climate, water may have persisted in underground reservoirs. Evidence from radar scans and rovers has revealed large deposits of subsurface ice, remnants of the planet's wetter past. These ice layers, some buried beneath protective layers of dust and rock, represent Mars's hidden water history. The presence of subsurface aquifers raises intriguing questions about whether life could still exist, buried beneath the surface and insulated from the harsh environment above. To understand Mars's watery history, it's essential to compare it to early Earth. Both planets began with similar ingredients: volcanic activity, water, and essential elements for life. However, their evolutionary paths diverged due to differences in size, gravity, and geological activity. Earth's tectonic plates recycled carbon dioxide, stabilizing the climate and supporting a long-term water cycle. Mars, with its smaller size and weaker gravity, lost its tectonic activity earlier, limiting its ability to sustain a stable climate. Despite these differences, Mars's ancient lakes and river systems bear a striking resemblance to early Earth environments. The deltas and sediment layers found in Martian craters are analogous to those on Earth during its Precambrian era, when microbial life flourished. These similarities suggest that Mars could have hosted life during its habitable phase, raising questions about the universality of life in the universe. Mars's ancient water story is also written in its rocks and minerals. Hydrated minerals, such as clays and sulfates, found across the planet's surface provide direct evidence of prolonged water activity. These minerals form in the presence of water, pointing to stable environments where water interacted with the Martian crust. Perchlorates, discovered in the soil by rovers, hint at briny water flows that may have persisted even as Mars became colder and drier. The discovery of silica and hematite-rich deposits further supports the theory that Mars once had liquid water with neutral to slightly acidic pH, conditions favorable for microbial life. Volcanic activity on Mars also played a significant role in shaping its water history. Eruptions released water vapor and other gases, contributing to a temporary greenhouse effect that warmed the surface. Evidence of ancient hydrothermal systems, places where heat from the planet's interior interacted with water, points to potential habitats for life. These hydrothermal vents, similar to those on Earth's ocean floor, could have provided the energy and nutrients necessary for life to thrive. While water once flowed freely on Mars, its availability wasn't uniform. Regional variations in Mars's landscape created diverse water systems, from vast oceans in the north to isolated lakes in craters. The southern highlands, with their higher elevation, likely hosted ice and small glacial systems, while the northern lowlands acted as basins for larger water bodies. These regional differences would have shaped Mars's climate and hydrology, creating a patchwork of environments with varying potential for habitability. The loss of water on Mars wasn't immediate. For millions of years, water may have cycled between the surface and underground reservoirs. Seasonal changes, driven by Mars's axial tilt, influence the stability of liquid water, creating transient rivers and lakes. Dust storms, a defining feature of modern Mars, likely played a role in redistributing water and affecting its long-term availability. The interplay between surface water and atmospheric loss created a dynamic system, one that eventually succumbed to the planet's harsh conditions. Mars's history as a watery world is more than a geological curiosity. It's a testament to the planet's potential to harbor life. If microbial life ever emerged on Mars, it would have found a home in its stable lakes, beneath its protective atmosphere, or near hydrothermal vents. Understanding these ancient environments is crucial for future missions as scientists search for biosignatures, chemical traces of life that may still be preserved in Martian rocks. As we explore Mars through rovers and orbiters, the story of its ancient water continues to unfold. Curiosity has uncovered clay-rich regions in Gale Crater, pointing to a long-lived lake environment. Perseverance is now exploring Jezero Crater, a former river delta, in search of signs of past life. Mars's transformation from a vibrant, water-rich world to the arid desert we see today is a reminder of how dynamic planets can be. Organic chemistry on Mars, building blocks of potential life. The discovery of organic molecules on Mars is not just a milestone, it is a doorway to understanding whether life once existed, or could still exist, on our planetary neighbor. Through advanced missions and tireless exploration, we have begun to unravel the chemical mysteries buried in Martian soil, rocks, and atmosphere. The groundbreaking detection of organic compounds by NASA's Curiosity rover in Gale Crater marked a significant leap forward in our understanding of Mars. In 2018, the rover unearthed a treasure trove of simple organic molecules trapped within ancient mudstones. These molecules, such as thiophanes and aliphatic hydrocarbons, are not definitive evidence of life, but serve as the building blocks for biological processes. Their discovery is significant because it proves that the chemical ingredients necessary for life were present on Mars billions of years ago. Curiosity's detection revealed that these molecules were preserved in sediments from an ancient lakebed, highlighting Gale Crater's potential as a once habitable environment. These organics could have originated from Martian biology, meteorite impacts, or even geological processes such as volcanic activity. Regardless of their origin, the finding challenges us to dig deeper into Mars's chemical history. Among the most debated discoveries on Mars is the presence of methane in its atmosphere. Methane is a volatile gas that, on Earth, is produced predominantly by biological activity. On Mars, the story is more complex. Seasonal fluctuations in methane levels have been detected by both the Curiosity rover and orbiters like the European Space Agency's Trace Gas Orbiter. These patterns suggest that methane is being released periodically, possibly from underground reservoirs. The source of Martian methane remains a mystery. It could arise from abiotic processes like serpentinization, where water interacts with certain minerals, or it could hint at microbial life lurking beneath the surface. The short lifespan of methane in Mars's atmosphere further complicates the puzzle, indicating recent or ongoing activity. Whether geological or biological, the presence of methane hints at a dynamic, active Mars. Volcanic activity on Mars has played a crucial role in shaping its chemical landscape. Billions of years ago, the planet was home to massive volcanic eruptions that released carbon dioxide, sulfur, and water vapor into the atmosphere. These elements created a rich chemical environment, potentially fostering prebiotic reactions necessary for life. Hydrothermal systems associated with volcanic activity may have provided energy and nutrient-rich conditions, similar to those found around Earth's deep-sea vents. These environments could have acted as chemical crucibles, where organic molecules formed and accumulated. The legacy of this activity is imprinted in Mars's basaltic rocks, which hold clues to the planet's fiery past and its potential for habitability. Mars's soil is rich in perchlorates, chemical compounds that have sparked both excitement and challenges in the search for organics. Discovered by NASA's Phoenix lander in 2008, perchlorates are highly reactive oxidizing agents that can break down organic molecules when heated. This characteristic makes it difficult to detect organics directly, as the compounds might decompose during analysis. Despite their destructive properties, perchlorates may also serve as a source of chemical energy for microbes. On Earth, certain extremophiles thrive by metabolizing perchlorates, suggesting that similar organisms could exist on Mars. These compounds are a paradox, both a hindrance to our investigations and a potential lifeline for Martian life. Mars's ancient magnetic field once played a vital role in protecting its surface from harmful solar radiation. This shield allowed organic molecules to form and persist on the planet's surface. However, when the magnetic field weakened and vanished approximately 4 billion years ago, Mars became vulnerable to cosmic rays and solar winds, which stripped away much of its atmosphere and surface organics. Today, any remaining organics on the Martian surface are likely buried beneath layers of rock and regolith, shielded from radiation. These subsurface environments, protected from harsh conditions, offer a promising refuge for life or its remnants. Future missions will likely focus on drilling into these hidden reservoirs to uncover their secrets. Mars's history of hydrothermal activity presents another tantalizing possibility for organic chemistry. Evidence suggests that ancient hydrothermal vents existed on the planet, providing a continuous source of heat and nutrients. These vents could have created localized environments conducive to prebiotic chemistry, where complex organic molecules formed and interacted. On Earth, similar hydrothermal systems are teeming with life, making them one of the most promising analogues for potential Martian ecosystems. Mars's surface has been bombarded by meteoritic impacts throughout its history, delivering a steady supply of organic-rich material from space. Carbonaceous chondrites, a type of meteorite, are known to contain amino acids and other organic compounds. These impacts may have deposited essential ingredients for life on the Martian surface, enriching its chemical inventory. High-energy impacts also generate heat and pressure, facilitating chemical reactions that can synthesize new organic molecules. Impact craters, such as Gale and Jezero, are thus not just geological landmarks, but also potential laboratories for studying prebiotic chemistry on Mars. The link between the amounts of oxygen and methane in Mars's atmosphere is one of the most fascinating findings of the past several years. A feature that has not been completely explained is the fact that Curiosity recorded seasonal changes in both gases at the same time. The intriguing prospect of microbial life is heightened when comparable connections on Earth are associated with biological processes. Photochemical processes triggered by ultraviolet light are one non-biological explanation, but there are others that hold water as well. These connections may give important information about the biological and chemical processes occurring on Mars, making their understanding an important goal for ongoing and future missions. Despite significant advancements, detecting organics on Mars remains a formidable challenge. The planet's oxidizing surface environment, dominated by reactive compounds like perchlorates, complicates direct analysis. Instruments must be capable of distinguishing between biological and abiotic sources, while avoiding contamination from Earth-based materials. Missions like Perseverance and the upcoming Mars Sample Return aim to address these challenges by collecting and analyzing pristine samples. These efforts represent a critical step toward unlocking the secrets of Martian organics. The role of Martian minerals, building blocks of life. For ages, the mysterious red planet Mars has captivated the imagination of mankind. The old rocks conceal a narrative, while the landscape and towering volcanoes appear desolate now. Phosphates, boron, sulfur, and iron are among the minerals buried beneath the rust-colored soil, which may have created the perfect setting for the first sparks of life. At the heart of life as we know it is RNA, the molecular precursor to DNA, and phosphate is an essential component of its structure. Phosphates provide the sturdy backbone for RNA molecules, making them indispensable for any scenario involving life's beginnings. Mars, it turns out, has an abundance of phosphate-bearing minerals like apatite, which have been discovered in Martian meteorites and analyzed by rovers like Curiosity and Perseverance. These minerals likely dissolved in ancient Martian waters, making phosphates bioavailable in concentrations that may have outpaced Earth's early environments. What sets Mars apart is its unique water chemistry billions of years ago. On Earth, much of the early phosphate may have been locked away in inaccessible mineral forms, but Mars's waters were rich in acidic solutions. This acidity likely dissolved phosphates, making them more readily available for chemical reactions. This distinct geochemical advantage might have allowed Mars to support prebiotic chemistry earlier than Earth. Another critical discovery on Mars was boron, an element essential for stabilizing ribose, the sugar molecule in RNA. In 2013, NASA's Curiosity rover detected boron in Martian rocks within Gale crater. Boron acts as a molecular stabilizer, preventing ribose from degrading in aqueous environments. Without it, ribose would disintegrate too quickly for more complex molecules to form. Interestingly, boron is relatively scarce on Earth, and its distribution in early environments was likely patchy. Mars, on the other hand, may have had more accessible borates thanks to its volcanic activity and unique mineral composition. This discovery raises a compelling question. Did Mars's natural abundance of boron make it a more favorable cradle for life's molecular precursors? Mars owes its iconic red hue to the abundance of iron on its surface. Hematite, magnetite, and other iron-rich minerals are scattered across the planet, forming the foundation of its geology. But iron wasn't just a geological feature. It may have been a biochemical catalyst. Iron's ability to drive redox reactions makes it a powerful enabler of prebiotic chemistry, facilitating the formation of amino acids and other organic molecules. Ancient Martian waters likely carried dissolved iron, creating a dynamic environment where organic molecules could form and interact. On Earth, hydrothermal vents are considered one of the most likely birthplaces of life due to similar iron-rich conditions. Mars's iron-rich environment, combined with its once-abundant water, mirrors these settings and suggests that similar processes could have unfolded on its surface. Sulfur, an essential element for life, is found in abundance on Mars. The planet's surface features sulfates and sulfides, minerals that are both reactive and essential for complex chemical reactions. Sulfur plays a pivotal role in metabolic processes, enzymatic reactions, and the synthesis of amino acids and proteins. On Mars, sulfur may have driven the chemistry necessary for early life. Sulfates are highly soluble in water, creating reactive environments that could facilitate the formation of organic molecules. Moreover, volcanic activity on Mars likely released sulfur into the atmosphere and ancient lakes, creating hotspots of chemical activity. These sulfur-rich regions may have been analogous to Earth's hydrothermal vents, cauldrons of chemical potential where life could take its first steps. Silicon, a major component of Martian rocks, adds another layer of intrigue to the planet's potential for fostering life. Silicate minerals, such as feldspar and quartz, provide reactive surfaces that can concentrate organic molecules. These surfaces act like natural laboratories, where molecules stick, interact, and form more complex compounds. Mars's volcanic history contributed to a diverse array of silicate minerals. As water flowed across its surface billions of years ago, it interacted with these minerals, creating dynamic chemical environments. Silicates may have provided a stable platform for early chemical reactions, shielding organic molecules from degradation and increasing their chances of forming into life's building blocks. Among the most significant discoveries on Mars are its vast deposits of clay minerals or phyllosilicates. These clays, found in regions like Gale crater and Jezero crater, are known catalysts for organic chemistry. On Earth, clays are thought to have played a crucial role in assembling simple molecules into larger, more complex structures like RNA and proteins. Martian chemical nodes would have been housed in the vast clay formations left by long-gone rivers and lakes. Because of their ability to absorb organic molecules, clays can concentrate them in small areas, increasing the likelihood of reactions. Fragile organic molecules may have found the stability they required to develop into the ancestors of life within the protective embrace of these clay particles. The geological stability of Mars is an enthralling feature. Much of Mars's old mineral record has survived, in contrast to Earth's surface, which is continually changing due to plate tectonics. Due to its relative stability, the early solar system may still be seen, providing information that the Earth's dynamic crust has long ago covered up. Mars's mineral wealth, combined with its stable geology, created a unique environment for chemical evolution. Its early oceans, acidic waters, and volcanic activity may have created a more favorable setting for prebiotic chemistry than Earth's more turbulent beginnings. If life did start on Mars, its geochemical advantages may have played a critical role. Volcanoes on Mars were chemical engines that produced more than just a dazzling display of fire and lava. The planet's sulfur dioxide, carbon dioxide, and water vapor atmospheres were formed by the planet's tremendous volcanic activity. Reactive habitats, rich in varied components, were created as a result of these gases interacting with the surface. Volcanic glass, a byproduct of eruptions, is particularly interesting. This material is highly reactive and can facilitate the assembly of organic molecules. On Mars, volcanic glass may have littered the landscape, creating countless microenvironments where life's chemistry could begin. The rocks of Mars provide evidence of the red planet's wet history, from hydrated minerals like gypsum to extensive systems of old riverbeds. In addition to being proof of water's presence, these minerals also serve as reservoirs, encasing liquid and dissolved organics inside their frameworks. These minerals may have maintained constant conditions necessary for the chemistry of life to endure in habitats when water was rare or fleeting. Hydrated minerals also point to an era when liquid water was abundant, creating lakes, rivers, and perhaps even oceans. These water-rich settings were chemical crucibles, mixing minerals, organics, and energy sources in ways that could lead to life. Mars's lack of tectonic activity has preserved its ancient mineral record, making it a time capsule of the early solar system. While Earth's crust has been recycled countless times, Mars's surface retains its primordial features. This preservation offers an unprecedented opportunity to study the conditions that may have given rise to life. Martian meteorites, messengers from a red planet. Martian meteorites are rare treasures, identified by their unique geochemical fingerprints, which match the composition of gases in Mars's atmosphere as measured by the Viking landers in the 1970s. These rocks, numbering fewer than 300, are fragments of Mars's crust that were blasted into space by asteroid or comet impacts. Over millions of years, some of these fragments traversed the solar system, eventually crossing Earth's orbit and surviving the fiery descent through our atmosphere. The discovery of Martian meteorites is a story of human ingenuity and luck. Among the most famous is ALH 84001, found in Antarctica in 1984. Its origins on Mars were only confirmed years later, and it soon became the centerpiece of intense scientific scrutiny. This meteorite and others like it are not just geological specimens, they are time capsules, preserving a record of conditions on Mars billions of years ago. Few Martian meteorites have generated as much excitement and debate as ALH 84001. This rock, estimated to be over 4 billion years old, contains carbonate globules that sparked widespread interest when NASA scientists announced in 1996 that these structures might be evidence of ancient Martian life. Using electron microscopy, researchers identified features resembling microfossils and magnetite chains similar to those produced by terrestrial bacteria. Could this meteorite contain the first tangible proof of life beyond Earth? The ramifications were immense. Skepticism, though, was soon to arise. Skeptics contended that the characteristics may have developed as a result of post-meteorite pollution or abiotic processes. Despite the passage of time and the publication of new analyses that shed light on the topic from different angles, the discussion has not ended. No matter what happens, ALH 84001 will remain an important piece of evidence in the hunt for extraterrestrial life and in the study of meteorites from Mars. The journey of Martian meteorites begins with violent cosmic events. Mars, like Earth, is no stranger to asteroid and comet impacts. These collisions release immense energy, enough to eject fragments of the Martian surface into space. Mars's relatively low gravity and thin atmosphere make it easier for rocks to escape its grasp compared to Earth. The process, while rare, has been modeled extensively, showing how debris from impacts can achieve escape velocity and enter interplanetary space. Once ejected, these rocks embark on a perilous journey. They must survive intense radiation, extreme temperatures, and the vacuum of space for millions of years before encountering Earth. Remarkably, some meteorites still contain traces of water-altered minerals and organic compounds, suggesting that conditions on Mars may have supported the chemistry necessary for life. The existence of Martian meteorites on Earth raises a tantalizing question. Could life have originated on Mars and been transported to Earth via meteorites? This idea is central to the Panspermia hypothesis, which posits that life, or the building blocks of life, can travel between planets, hitching rides on spacefaring rocks. Laboratory experiments have shown that microbial life can survive the intense heat of atmospheric entry and the harsh conditions of space when shielded within rocks. If life existed on Mars during its early habitable phase, meteorite transfer could have provided a pathway for Martian microbes to seed life on Earth. Conversely, Earth-based life could have been transported to Mars. Not all Martian meteorites are the same. Scientists classify them into three main groups: shergottites, knucklites, and chassignites. Each type provides unique insights into Mars's geological history. Shergottites, the most common, are volcanic rocks formed within the last 500 million years, offering glimpses into Mars's more recent past. Knucklites, on the other hand, are older and contain evidence of water alteration, pointing to interactions with liquid water on Mars's surface or subsurface. Chassignites, the rarest group, reveal information about Mars's mantle composition. These classifications highlight the diversity of Martian meteorites and underscore their value as records of the planet's evolution. Together, they paint a picture of a dynamic world that once had active volcanoes, flowing water, and a thicker atmosphere. The finding of organic compounds in meteorites from Mars is one of the most fascinating findings in this field. Several meteorites, notably ALH 84001, have been found to contain these carbon-based chemicals which are vital to life as we know it. Yet, their provenance is a matter of heated controversy. Do you think these organics are the product of abiotic Martian processes or the remains of a bygone Martian civilization? Is it also possible that they were exposed to meteorites after touching down on Earth? Advanced analytical techniques, such as isotopic analysis, have provided some answers, but also raised new questions. For example, the isotopic signatures of certain organic molecules suggest they originated on Mars, strengthening the case for indigenous Martian chemistry. Yet, the possibility of contamination cannot be entirely ruled out, illustrating the challenges of interpreting these enigmatic samples. Beyond the search for life, Martian meteorites offer invaluable information about Mars's ancient environment. Traces of water-altered minerals and trapped atmospheric gases provide direct evidence that Mars once had liquid water and a thicker atmosphere. These findings align with observations from Mars rovers and orbiters, which have identified river valleys, deltas, and other features indicative of a wetter past. Research into meteorites has also shown that, throughout the course of billions of years, Mars's environment changed substantially. From what appears to be a warm and humid planet now, it was most likely turned into a cold and dry one due to volcanic eruptions, the planet's magnetic field vanishing, and atmospheric erosion caused by solar winds. Scientists can better piece together Mars' past and assess the red planet's habitability if they have a better grasp of these processes. Studying Martian meteorites is no small feat. These rocks are rare, and their journey through space and time has left them altered in ways that complicate analysis. Contamination from Earth's environment is a persistent challenge, as is the difficulty of determining the age and origin of specific features within the meteorites. Despite these hurdles, advances in technology continue to yield new insights. For example, modern spectroscopic techniques have revealed details about the mineralogy and chemistry of Martian meteorites that were previously inaccessible. The rewards of this research are immense. Martian meteorites are not just geological specimens, they are windows into the past, offering clues about the conditions that shaped Mars and potentially fostered life. They also serve as stepping stones for future exploration, guiding the design of Mars missions and informing the search for biosignatures on the red planet. The study of Martian meteorites is far from over. As scientists continue to analyze existing specimens and discover new ones, the mysteries of Mars will gradually come into sharper focus. Upcoming Mars sample return missions promise to provide fresh context for interpreting meteorite findings, potentially resolving long-standing debates and opening new avenues of inquiry. The Panspermia hypothesis. Did life travel from Mars to Earth? For centuries, humanity has pondered the origins of life on Earth. But what if the story of life began elsewhere, on a neighboring world, hurtling through space to seed our own planet? This is the intriguing premise of the Panspermia hypothesis, a theory that suggests life or its precursors may travel between planets, carried by meteorites or even propelled by cosmic forces. Panspermia, meaning seeds everywhere, was first conceptualized by the ancient Greek philosopher Anaxagoras. Yet its scientific foundation took root much later, when thinkers like Svante Arrhenius proposed that microscopic life could travel between celestial bodies, propelled by radiation pressure. Over the years, the theory evolved, with variations such as lithopanspermia, life traveling via rocks, radiopanspermia, life propelled by radiation, and even directed panspermia, the idea of life deliberately spread by advanced civilizations. Modern science, equipped with tools like space probes and particle accelerators, has reinvigorated this age-old theory. With evidence of organic molecules on comets, extremophiles surviving space-like conditions, and Martian meteorites bearing hints of organic compounds, panspermia is no longer confined to the realm of speculation. The journey of life between planets is fraught with peril. Space is a vacuum, bombarded by radiation and subjected to extreme temperatures. Yet, certain microorganisms on Earth, extremophiles, seem almost custom-built for such journeys. Take Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium for its remarkable resilience to radiation. It has survived doses of radiation thousands of times higher than what would kill a human. Then there are tardigrades, tiny creatures known as water bears, which have endured the vacuum of space unscathed. These hardy organisms provide proof of concept that life can endure the conditions of interplanetary transit. Laboratory experiments have further bolstered this possibility. NASA's Long Duration Exposure Facility, LDEF, and ESA's Biopan missions exposed microbial spores to space-like conditions, finding that some survived prolonged exposure. Encased within meteorites or ice, these microorganisms could be shielded from radiation, significantly enhancing their survival odds. The mechanics of panspermia hinge on one critical process: the ejection of material from a life-hosting planet into space. This is where cosmic impacts come into play. When a large asteroid or comet strikes a planet, it can send debris flying into space at incredible velocities. On Mars, with its lower gravity compared to Earth, this process is even more efficient. Simulations show that fragments of Mars's surface containing potential microbes or organic molecules could easily escape its gravitational pull. Once ejected, these fragments become cosmic travelers, drifting through the solar system. Some of this Martian debris has made its way to Earth, as evidenced by meteorites like ALH 84001. These space rocks carry chemical and isotopic signatures uniquely Martian, showing that material exchange between planets is not just possible, but has occurred. How panspermia fits in with the schedules of habitable planets is one of the most intriguing parts of the theory. Mars cooled more rapidly than Earth, which means that it may have become habitable sooner. The early appearance of life on Earth might be explained by the transport of germs from Mars to Earth via meteorites, assuming this is indeed the case. Studies suggest that Martian material ejected by impacts could reach Earth in tens of thousands of years, short enough for hardy microorganisms to survive the journey. Some fragments could even remain in stable orbits for millions of years, creating opportunities for multiple waves of transfer. Martian meteorites like ALH 84001 have long captured the imagination of scientists and the public alike. Discovered in Antarctica, this meteorite contains tiny structures that some researchers interpret as microfossils, while others attribute them to non-biological processes. Whether or not these features represent ancient Martian life, the very existence of such meteorites proves that material from Mars can travel to Earth. Beyond ALH 84001, other Martian meteorites have revealed traces of organic molecules, including polycyclic aromatic hydrocarbons, PAHs. These findings suggest that Mars once harbored the building blocks of life. The hostile atmosphere of space is a big obstacle for panspermia. Organic molecules can be degraded and microbes killed by cosmic radiation and UV light. However, meteorites do offer some natural defense. The majority of radiation may be absorbed by the exterior layers of a rock, protecting its inside. Studies have shown that microbial spores embedded in rocks or ice can survive simulated space conditions. These findings align with the hypothesis that life could hitch a ride across the cosmos, encased in protective material. Panspermia, despite its allure, is not without skeptics. Critics argue that there is no direct evidence of microbial life on Mars or other celestial bodies, making the hypothesis speculative. They also question whether microorganisms could survive the intense heat of atmospheric re-entry. Counter-arguments abound. For one, extremophiles on Earth demonstrate that life can survive extreme conditions. Additionally, some meteorites retain material from their interiors, largely unaltered by re-entry, suggesting that embedded microorganisms could also survive. While Mars is the leading candidate for panspermia involving Earth, the hypothesis extends beyond our planetary neighbor. Comets, with their reservoirs of water ice and organic molecules, may also play a role. Missions like Rosetta, which studied Comet 67P/Churyumov-Gerasimenko, have detected complex organics, suggesting that comets could deliver life's building blocks to planets. Europa and Enceladus, two icy worlds having seas under their surfaces, may also function as nodes in a network of panspermia. Impacts have the potential to release materials into space, perhaps seeding neighboring planets, if life is present under their ice surfaces. A more speculative branch of the theory is directed panspermia, the idea that life was intentionally spread by an advanced civilization. While there is no evidence to support this notion, it raises intriguing philosophical questions. If humanity ever faces extinction, could we ensure the survival of life by seeding other planets? Directed panspermia also offers a testable framework. Unusual isotopic ratios or engineered biomolecules in extraterrestrial samples could point to artificial origins. Panspermia challenges our Earth-centric view of life's origins. If life can travel between planets, the cosmos becomes a much more interconnected web of potential habitats. This has profound implications for astrobiology, suggesting that life may be more common and more resilient than previously thought. As missions like Mars Sample Return and Europa Clipper prepare to collect and analyze extraterrestrial material, we may soon have the tools to test panspermia directly. Early microbial life. Earth versus Mars. Mars and Earth share similar origins, having formed around 4.5 billion years ago from the same primordial dust cloud. However, their evolutionary timelines diverged dramatically. Mars, being smaller and farther from the Sun, cooled more quickly than Earth. Geological evidence suggests that Mars entered a period of relative stability as early as 4.1 billion years ago. During this time, liquid water flowed on its surface, supported by a thick atmosphere that retained heat and pressure. Earth, on the other hand, was still in chaos. For the first several 100 million years, Earth was a molten hellscape, battered by asteroids and enveloped in toxic gases. It wasn't until around 3.9 billion years ago, during the tail end of the late heavy bombardment, that Earth began to stabilize. This lag in habitability gives Mars an intriguing edge in the timeline for life's emergence. Could Mars have nurtured life while Earth was still uninhabitable? On Earth, the earliest evidence of life comes from fossilized microbial mats known as stromatolites, dating back 3.5 billion years. These structures were created by colonies of cyanobacteria that thrived in shallow, sunlit waters. Stromatolites not only reveal the presence of life, but also showcase its adaptability. These early microbes were extremophiles, capable of surviving in environments with intense UV radiation, extreme heat, and limited oxygen. Mars, too, had conditions that could have supported extremophiles. During its early habitable window, the planet featured flowing rivers, vast lakes, and perhaps even an ocean in its northern hemisphere. The presence of volcanic activity would have provided heat and energy, while the planet's iron-rich soil could have facilitated chemical reactions essential for life. If microbial life did emerge on Mars, it likely resembled Earth's early extremophiles, thriving in environments shaped by volcanic and hydrothermal activity. Water is a cornerstone of life as we know it, and its presence on both Earth and Mars is key to understanding their potential for life. Earth's vast oceans served as incubators for early microbial life, shielding it from harmful UV radiation and providing a stable environment for chemical reactions. Mars, while lacking Earth's expansive seas, had its own reservoirs of liquid water. Ancient river valleys, lake beds, and deltas are etched into the Martian surface, offering a glimpse into a wetter past. The question is how long Mars could sustain liquid water. Its smaller size and weaker gravity made it difficult for the planet to hold on to its atmosphere. As its magnetic field dissipated, solar winds stripped away the atmosphere, causing surface water to evaporate or freeze. Yet, evidence of subsurface ice and hydrated minerals suggests that liquid water persisted long enough for life to potentially take hold. Life requires more than water. It needs energy. On Earth, early life harnessed energy through photosynthesis, chemosynthesis, or geothermal heat. Chemosynthetic microbes, in particular, relied on chemical reactions involving sulfur, iron, and hydrogen to generate energy. These microbes thrived in deep-sea hydrothermal vents and volcanic hot springs, environments rich in minerals and chemical gradients. Mars offered similar energy sources. Its volcanic activity, now dormant, would have created hot springs and hydrothermal vents, providing heat and nutrients. Iron and sulfur compounds in the Martian soil could have supported chemosynthetic organisms. The planet's thinner atmosphere also allowed more UV radiation to reach the surface, potentially driving unique photochemical reactions. While Earth was protected by its magnetic field and thick atmosphere, Mars lacked such defenses. As its core cooled and its magnetic field vanished, the Martian surface became vulnerable to solar and cosmic radiation. This poses a significant challenge for life on the surface. However, life could have found refuge underground. Subsurface environments, insulated by layers of rock and soil, would have been shielded from radiation and could have provided stable conditions for microbial communities. On Earth, extremophiles like Deinococcus radiodurans demonstrate the resilience of life in high radiation environments. These microbes repair DNA damage caused by radiation, offering a potential model for how Martian life might have adapted. Subsurface ice and brines on Mars could still harbor microbial life, preserved in isolated pockets where radiation cannot reach. When it comes to fossil evidence, Earth has an undeniable advantage. Ancient stromatolites and microfossils provide direct proof of early microbial life. These fossils are often found in sedimentary rocks, where minerals have preserved the structures of microbial colonies. On Mars, the search for fossils is far more challenging. The planet's surface is exposed to constant erosion from wind and radiation, which degrades organic materials over time. Nevertheless, Mars rovers like Curiosity and Perseverance are equipped to detect biosignatures, chemical or structural markers of life. Clay minerals, silica deposits, and carbonate rocks on Mars are promising targets for finding preserved organic molecules. If microbial life existed on Mars, its fossils may still be hidden in the planet's ancient lake beds or underground. While both planets had the necessary ingredients for life, their long-term habitability diverged sharply. Earth's active geology and plate tectonics continuously recycled nutrients and maintained a dynamic climate. Mars, with its static crust and lack of tectonic activity, relied on volcanic outgassing and chemical weathering to sustain its environment. This difference likely influenced the complexity and persistence of life on each planet. Earth's oceans provided a stable, long-term habitat for life to evolve, while Mars's habitability was shorter and more episodic. The planet's rapid loss of atmosphere and water likely limited the window for life to develop beyond the microbial stage. However, if life did emerge on Mars, it may have left behind traces that await discovery. Among the more fascinating theories is the idea that Martian and earthly life may have originated from the same place. Panspermia is the idea that proposes the possibility of life or its components being transported to other planets via meteorites. It is possible that rocks with microorganisms on them were thrown into space by impacts on Mars and then crashed into Earth. Did life first emerge on Mars and then make its way to Earth? That is the intriguing question that this intergalactic interchange begs. Martian meteorites found on Earth, such as ALH 84001, contain organic molecules and mineral formations that some scientists interpret as potential biosignatures. While these findings remain controversial, they highlight the interconnectedness of our solar system and the possibility that life on Earth may owe its existence to Mars. From its early days as a warm, wet world to its current state as a frozen desert, Mars challenges us to rethink the conditions necessary for life and the resilience of biology. Whether Mars was a failed experiment in life or an alternate cradle of creation. Water, the lifeblood of habitability. The importance of liquid water lies in its ability to dissolve and transport nutrients, facilitating the chemical reactions necessary for life. Its polarity enables it to act as a universal solvent, breaking down molecules and forming the basis for biological processes. Beyond its chemical properties, water's high heat capacity stabilizes climates, creating environments where life can thrive. If life ever existed on Mars, it would have required liquid water to sustain it, making the search for water a cornerstone of Martian exploration. Billions of years ago, Mars was a very different planet. Geological evidence suggests that vast oceans once sprawled across its surface. Scientists estimate that an ancient Martian ocean could have covered up to 20% of the planet's surface, with depths reaching thousands of meters. These waters likely pooled in the planet's northern hemisphere, where topographic features suggest the presence of low-lying basins, capable of holding immense volumes of liquid water. But where did it all go? Over time, Mars's thin atmosphere and weak gravity allowed much of its water to escape into space or freeze beneath the surface. Mars is far from dry. Subsurface ice deposits, identified by radar instruments aboard orbiters like the Mars Reconnaissance Orbiter, reveal vast reservoirs of frozen water. Seasonal cycles show water vapor in Mars's atmosphere, rising and falling with changes in temperature. Perhaps most intriguingly, the European Space Agency's Mars Express mission detected what appears to be a subsurface lake of briny water beneath the planet's south polar ice cap. This discovery has reignited hopes of finding extant life, as such environments may provide refuge from Mars's harsh surface conditions. Our robotic explorers have provided compelling evidence of Mars's watery past. The Curiosity rover discovered ancient streambeds in Gale Crater, with rounded pebbles indicating that water once flowed rapidly across the surface. In Jezero Crater, The Perseverance rover has been studying what was once a vast delta, where rivers deposited sediments into a long-gone lake. Meanwhile, Opportunity uncovered hematite blueberries, small mineral spheres formed in liquid water, further supporting the idea of prolonged wet conditions. Mars's surface is etched with features that speak of a water-rich past. The Valles Marineris Canyon system, the largest in the solar system, stretches over 4,000 kilometers and was likely carved by water erosion. Ancient deltas and river valleys, such as those in the Eberswalder and Jezero craters, point to persistent flowing water that could have supported life. Layered sediments found in these regions are similar to those seen on Earth, where water creates and preserves habitable niches. Mars's surface is rich in hydrated minerals, which form in the presence of water. Clay minerals detected by orbiters and rovers suggest that water persisted long enough to alter the planet's rocks chemically. Sulfates, another water-formed mineral, indicate the presence of acidic water environments in Mars's past. These hydrated minerals not only point to ancient water, but also serve as prime targets for future missions seeking signs of life. The chemical composition of Mars's ancient water is another key to understanding its habitability. Evidence suggests that early Martian water was less salty than it is today, with salinity levels conducive to life. However, as the planet dried out, its remaining waters became highly saline, similar to Earth's hypersaline environments like the Dead Sea. The pH of Martian water is thought to have ranged from neutral to slightly acidic, conditions that would still have been favorable for microbial life. These findings help scientists narrow down the types of organisms that might have thrived on ancient Mars. One of water's most important roles is its ability to preserve signs of life. On Earth, sedimentary rocks formed in water-rich environments often contain fossils and other biosignatures. On Mars, similar sedimentary formations have been identified, particularly in ancient lakebeds and deltas. If life ever existed on Mars, these water-altered rocks could hold the key to its discovery. The upcoming Mars sample return mission aims to bring some of these samples back to Earth for detailed analysis, potentially providing the first direct evidence of Martian life. Billions of years ago, Mars may have had a functioning hydrological cycle, complete with precipitation, evaporation, and groundwater flow. This cycle would have supported a dynamic climate, with rain filling lakes and rivers and groundwater seeping through the planet's porous crust. However, as Mars's atmosphere thinned and its magnetic field disappeared, this cycle would have collapsed, leaving the planet cold and arid. Understanding this transition is critical for piecing together Mars's climatic history. Mars's decline from a wet, warm world to a frozen desert is largely attributed to atmospheric loss. Without a strong magnetic field to shield it, Mars's atmosphere was gradually stripped away by solar winds. This loss of atmospheric pressure made it impossible for liquid water to remain stable on the surface, forcing it to evaporate or freeze. Isotopic analysis of hydrogen in Martian water vapor reveals that much of the planet's original water has escaped into space, leaving only traces behind. Mars and Earth share a surprising number of similarities in their early histories. Both planets had liquid water, active volcanism, and thick atmospheres. However, Earth's tectonic activity and persistent magnetic field allowed it to retain its water and develop stable climates over billions of years. In contrast, Mars's smaller size and weaker gravity made it more vulnerable to atmospheric loss and cooling. Despite these differences, the parallels between the two planets offer valuable insights into the conditions necessary for life. Even today, Mars may harbor pockets of habitable environments. Subsurface brines, protected from surface radiation by layers of rock and ice, could provide refuge for microbial life. On Earth, organisms have been found thriving in similar conditions, such as deep underground or in high salinity lakes. These analogues give scientists hope that life could persist on Mars, even in its current state. Upcoming missions aim to drill into the planet's subsurface, where ice and brine reservoirs are thought to exist. These efforts will not only help us understand Mars's climate history, but also assess its potential for past or present life. The discovery of water on Mars has profound implications for human exploration as well, as it could be used to support future colonies by providing drinking water and fuel. Mars's history of water expands our understanding of what makes a planet habitable. By studying Mars, scientists can refine their criteria for identifying habitable exoplanets, focusing on features like liquid water and stable climates. The lessons learned from Mars also remind us of the fragility of planetary environments and the factors that sustain life. Martian atmosphere and its evolution. Billions of years ago, Mars looked vastly different. It was a planet with rivers, lakes, and possibly even an ocean in its northern hemisphere. To support these liquid water features, Mars would have needed a thick atmosphere, rich in carbon dioxide and water vapor. This dense envelope of gases trapped heat, creating a greenhouse effect that kept surface temperatures warm enough for water to flow freely. Mars's early atmosphere was likely similar to a young Earth's, containing essential ingredients for life. The evidence of ancient river deltas, sedimentary layers, and dried lake beds points to a time when Mars could have been a cradle for microbial life. But the question remains, what happened to this once thick atmosphere? Unlike Earth, which still boasts a strong magnetic field, Mars's magnetic dynamo, generated by the movement of molten metals in its core, shut down billions of years ago. Without this magnetic shield, Mars was left vulnerable to the relentless assault of solar winds. These streams of charged particles from the Sun bombarded the planet, stripping away its atmosphere molecule by molecule. Data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, confirmed the rate at which solar winds continue to erode the Martian atmosphere. Over time, this process thinned the atmosphere to a point where surface pressure dropped to less than 1% of Earth's, leaving water unable to remain stable on the surface. Solar winds alone didn't cause Mars's dramatic transformation. High-energy ultraviolet radiation from the Sun also played a role, breaking apart atmospheric molecules like carbon dioxide and water. This photodissociation split water into hydrogen and oxygen. The lighter hydrogen atoms, unbound by gravity, escaped into space, while oxygen either bonded with surface minerals or drifted away more slowly. The isotopic composition of Mars's atmosphere tells the story of this escape. Heavier isotopes of elements like carbon and oxygen dominate the current atmospheric mix, as the lighter isotopes were preferentially lost to space. These isotopic ratios serve as a fingerprint of atmospheric erosion, allowing scientists to reconstruct the timeline of Mars's transformation. Mars's smaller size compared to Earth played a significant role in its atmospheric evolution. Its size meant that the planet cooled rapidly, leading to the solidification of its core and the cessation of volcanic activity. This cooling not only shut down the magnetic dynamo, but also reduced the outgassing of volcanic gases, which would have replenished the atmosphere. Volcanoes like Olympus Mons once released massive amounts of carbon dioxide, sulfur dioxide, and water vapor into the air, contributing to a thick, life-supporting atmosphere. But as volcanic activity dwindled, so did the planet's ability to maintain its atmospheric density. While Mars's atmosphere is now thin, it is still dynamic. Seasonal dust storms, some of which envelop the entire planet, play a significant role in shaping its atmospheric behavior. These storms lift dust particles high into the atmosphere, where they interact with water vapor and other trace gases. This process accelerates the loss of water by allowing solar radiation to break apart water molecules more efficiently. Dust storms also create temperature fluctuations and pressure changes, showcasing the interplay between the Martian surface and its atmosphere. Although these storms are not as impactful as ancient processes, they offer a glimpse into the planet's ongoing atmospheric evolution. Mars's polar ice caps, composed of water and carbon dioxide ice, act as seasonal reservoirs for its atmosphere. During the Martian summer, CO2 sublimates from the polar caps into the atmosphere, temporarily increasing its density. In winter, This gas refreezes at the poles, creating a cycle that affects surface pressure and weather patterns. As the atmosphere thinned, water either escaped into space or became trapped underground and in the polar ice caps. Some scientists speculate that subsurface reservoirs of liquid water may still exist, protected from the harsh surface conditions by layers of rock and ice. Methane detection on Mars has added a layer of intrigue to the story of its atmosphere. Observations by the Curiosity rover and orbiters like the Trace Gas Orbiter have recorded seasonal variations in methane levels. This fluctuation hints at potential geological or even biological sources. Methane is a molecule that can be produced by microbial life, volcanic activity, or chemical reactions involving water and minerals. Its presence in the Martian atmosphere, albeit in trace amounts, raises questions about the planet's past and present habitability. The evolution of Mars's atmosphere offers a stark contrast to Earth's. Earth's magnetic field and active geology have preserved a dense, life-supporting atmosphere over billions of years. Plate tectonics recycle carbon dioxide, maintaining a stable climate, while the magnetic field shields the atmosphere from solar winds. Mars, lacking these protective and regenerative mechanisms, underwent a rapid decline. By studying these differences, scientists gain a deeper understanding of the delicate balance required for long-term habitability. Mars's atmospheric history serves as a cautionary tale for planets in similar situations. Exoplanets orbiting close to their stars may face atmospheric erosion similar to Mars if they lack strong magnetic fields. Future missions to Mars aim to uncover more details about its atmospheric evolution. Instruments capable of analyzing subsurface gases, isotopic ratios, and ancient rocks could provide the missing pieces to this complex puzzle. Geological evidence of ancient life on Mars. NASA's Mars rovers have been at the forefront of discovering geological evidence that suggests Mars was once a haven for water, a key ingredient for life. Curiosity, which has been exploring Gale Crater since 2012, uncovered evidence of ancient lake beds. The sedimentary layers analyzed by Curiosity suggest that liquid water persisted on the Martian surface for millions of years. Clay and sulfate minerals discovered in the crater point to a stable environment with neutral pH levels, ideal for sustaining microbial life. The Perseverance rover, currently exploring Jezero Crater, has expanded on these discoveries. Jezero Crater is home to what appears to be an ancient river delta, a site where water once deposited sediment over time. Perseverance has been drilling rock cores and analyzing samples, revealing the presence of carbon-based molecules. These discoveries are particularly exciting because deltas are known on Earth to trap and preserve organic material, making Jezero an ideal location to search for biosignatures. Meanwhile, orbiters like the Mars Reconnaissance Orbiter, MRO, have provided a broader context by mapping the planet's surface. Using high-resolution imaging and spectrometry, MRO has identified widespread hydrated minerals, including clays and sulfates, further supporting the theory that Mars once had an abundance of water. These hydrated minerals, often linked to long-standing water activity, are critical in the preservation of organic compounds. Sedimentary rocks on Mars serve as a natural archive of the planet's history, preserving the conditions of their formation. Layers within these rocks reveal a timeline of Mars' environmental changes, from wet and habitable to the dry and arid conditions we see today. Mudstones, for instance, are fine-grained sedimentary rocks that have been identified by both Curiosity and Perseverance. These rocks form in still water environments, such as lake beds, and are known to trap organic molecules. Their discovery suggests that lakes on Mars existed long enough to create stable conditions conducive to life. Another critical aspect of Mars's geology is the presence of clay deposits. Found in regions like Maweth Vallis and Gale Crater, clays form through prolonged interaction between water and volcanic rock. Clays are particularly significant because they not only form in wet environments, but also have the unique ability to preserve organic molecules over billions of years. These minerals act as a protective shield, preventing the degradation of delicate biosignatures. The search for evidence of ancient life on Mars has also extended to meteorites that originated from the planet and eventually landed on Earth. Among the most famous is ALH 84001, a Martian meteorite discovered in Antarctica. This meteorite contains microscopic structures that some scientists believe resemble fossilized nanobacteria. Additionally, magnetite crystals found within ALH 84001 are arranged in patterns similar to those produced by biological processes on Earth. However, skepticism remains, with critics arguing that these features could result from abiotic chemical reactions rather than biological activity. Perseverance has also begun to examine Martian rocks with similar potential. Textures resembling stromatolites, layered formations created by microbial mats on Earth, have been observed in some Martian rocks. While these textures could be geological in origin, their resemblance to Earth's biosignatures makes them compelling targets for future studies. Comparing Martian geological features to terrestrial analogues has been invaluable in identifying potential signs of life. Stromatolites on Earth, found in regions like Shark Bay, Australia, are among the oldest known biosignatures, dating back over 3.5 billion years. These structures form when microorganisms trap and bind sediment, creating layered rock formations. If similar structures exist on Mars, they could indicate that microbial life once thrived there. Chemical biosignatures also provide critical evidence. On Earth, the isotopic ratios of carbon and nitrogen in organic molecules often point to biological origins. Mars rovers have detected variations in these isotopes, particularly in methane emissions, sparking debates about whether the source could be biological or geological. Methane's presence on Mars is especially intriguing because on Earth, a significant portion of methane is produced by living organisms. Despite these promising signs, interpreting evidence of life on Mars comes with significant challenges. One of the most pressing issues is the difficulty in distinguishing between biological and abiotic processes. For example, certain chemical reactions involving water and volcanic rock can produce organic molecules or structures that mimic biosignatures. This ambiguity complicates efforts to draw definitive conclusions. Contamination also poses a major hurdle. Despite rigorous sterilization protocols, there is always a risk that Earth-based microbes could inadvertently contaminate Martian samples. This concern has driven the design of upcoming missions, including plans for returning Martian samples to Earth for analysis under highly controlled conditions. Moreover, the harsh surface conditions on Mars today, radiation, extreme cold, and lack of a protective magnetic field, make it unlikely that any surface biosignatures would remain intact. Subsurface exploration may be required to uncover well-preserved evidence. The quest for geological evidence of ancient life on Mars is far from over. Perseverance is actively collecting samples that will eventually be returned to Earth through a collaboration between NASA and the European Space Agency. These samples represent our best chance to conduct detailed laboratory analyses, using techniques far beyond the capabilities of current rover instruments. Another exciting new area to explore is the subsurface. Future missions may use deeper drilling technology to access radiation-protected elements, while present rovers can only drill a few centimeters into the surface. It is also more probable that organic molecules and water ice will be retained in subsurface conditions. Regions with evidence of hydrothermal activity, such as the Tharsis and Elysium volcanic provinces, are particularly intriguing. On Earth, hydrothermal vents support rich ecosystems, suggesting that similar environments on ancient Mars could have been hotspots for microbial life. Sending humans to Mars could change the way we look for fossils of extinct organisms. The efficiency of scientific studies would be greatly enhanced if astronauts could reach varied terrains and decide in real time where to gather samples. Humans armed with sophisticated technology and able to pivot in response to ground-level discoveries might develop solutions that machines cannot. The search for geological evidence of ancient life on Mars is a story of perseverance, both in the rovers exploring the planet and in humanity's relentless drive to understand our place in the cosmos. Why Mars and not Venus? A comparative exploration of habitability. Venus and Mars, two planets that couldn't be more different today, each hold clues to understanding the delicate balance required for planetary habitability. Venus is a fiery inferno with surface temperatures capable of melting lead, while Mars is a frozen desert with vast stretches of barren land. Yet billions of years ago, both planets may have shared a similar potential for supporting life. What caused their paths to diverge so dramatically? And why does Mars, rather than Venus, remain a more compelling target in the search for ancient habitability? Billions of years ago, Venus may have been an oasis of calm. Evidence suggests that the planet once had liquid water, possibly forming shallow oceans that lasted for hundreds of millions of years. With a thick carbon dioxide atmosphere and abundant sunlight, Venus could have harbored a climate conducive to the early building blocks of life. But this paradise was not to last. Venus's proximity to the Sun subjected it to intense solar radiation, which began to evaporate its surface water. Water vapor, a potent greenhouse gas, trapped even more heat, accelerating the warming process in a runaway feedback loop. Over time, the planet's oceans boiled away entirely, releasing more carbon dioxide into the atmosphere as water ceased to moderate the climate. Ultraviolet radiation from the Sun further compounded Venus's problems by breaking apart water molecules in the atmosphere. This allowed lighter hydrogen atoms to escape into space, leaving the planet permanently arid. Today, Venus's thick atmosphere of carbon dioxide traps immense amounts of heat, creating a surface temperature hotter than any other planet in the solar system. Things went downhill for Mars. Being the fourth planet from the Sun meant that it got less sunlight than either Venus or Earth. The presence of ancient riverbeds, deltas, and lake beds discovered by rovers and orbiters provides evidence that water was able to remain on the surface for extended periods of time due to this colder climate. Martian temperatures were formerly high enough to sustain liquid water because of the presence of a thicker atmosphere heavy with carbon dioxide. But Mars was dealt a poor hand from the start. Being smaller than both Earth and Venus, Mars couldn't hold on to its internal heat or sustain significant tectonic activity for long. Its smaller mass also limited its ability to maintain a magnetic field. Without this protective shield, the solar wind gradually stripped away Mars's atmosphere, leaving it thin and unable to support surface water. Over time, the planet cooled, and its remaining water either froze beneath the surface or sublimated into the atmosphere. Mars's transition from a potentially habitable planet to the barren world we see today serves as a stark reminder of how fragile habitability can be. While Venus became too hot, Mars became too cold. This Goldilocks problem has profound implications for understanding planetary evolution. Size matters when it comes to planetary habitability. Venus and Earth are nearly identical in size and mass, giving them similar abilities to retain atmospheres and sustain internal heat through radioactive decay. This geological activity helps recycle carbon dioxide into rocks and maintain a stable climate over billions of years. Mars, on the other hand, is much smaller, about half the diameter of Earth and only 10% of its mass. Its weak gravity made it easier for atmospheric gases to escape into space. Additionally, its smaller size caused its internal heat to dissipate quickly, halting volcanic activity and tectonic processes that could have replenished its atmosphere. Without these mechanisms, Mars was unable to maintain the conditions necessary for long-term habitability. Venus's atmosphere is a crushing blanket of carbon dioxide, with a surface pressure 90 times greater than Earth's. This dense atmosphere is both a product and a cause of the planet's extreme heat, trapping solar energy in a perpetual greenhouse effect. Clouds of sulfuric acid swirl through its skies, reflecting sunlight and adding to its inhospitable nature. Mars's atmosphere, by contrast, is tenuous and thin, with less than 1% of Earth's atmospheric pressure. Made mostly of carbon dioxide, it lacks the density to trap heat effectively, leading to the planet's cold temperatures. Mars's thin atmosphere also offers little protection from solar radiation, further diminishing its ability to support life on the surface. The differences in atmospheric density and composition between Venus and Mars are critical to understanding why they evolved so differently. While Venus's thick atmosphere fueled a runaway greenhouse effect, Mars's inability to hold onto its atmosphere led to its transformation into an icy wasteland. The distance of a planet from its star plays a key role in determining its climate and habitability. Venus orbits at approximately 0.72 astronomical units (AU) from the Sun, placing it on the inner edge of the habitable zone. This proximity means it receives nearly twice as much solar energy as Earth, a factor that likely contributed to the evaporation of its early oceans and the onset of its greenhouse effect. Mars, on the other hand, orbits at 1.52 AU on the outer edge of the Sun's habitable zone. It receives significantly less solar energy, which helped it avoid the runaway greenhouse effect that doomed Venus. However, this reduced energy input also made it more difficult for Mars to sustain a warm, wet climate, especially after losing much of its atmosphere. These divergent paths highlight the importance of a planet's position within the habitable zone. Venus demonstrates the dangers of being too close to a star, while Mars underscores the challenges of being too far away. Venus remains geologically active today, with evidence of recent volcanic eruptions detected by spacecraft. This activity continues to pump carbon dioxide into its atmosphere, sustaining its inhospitable conditions. However, the absence of plate tectonics, a key feature of Earth's geology, means that Venus lacks a mechanism to recycle carbon dioxide into its crust. This may have been a critical factor in its climatic downfall. In contrast, Mars's geology has been dormant for eons. Relics of a more active history may be seen in its huge volcanoes, such as Olympus Mons. A factor in Mars's cooling and atmospheric loss, the outgassing of greenhouse gases came to a stop when the planet's volcanic activity ceased. The planet's inability to support complex cycles necessary for life was further exacerbated by the absence of geological activity. The contrasting fates of Venus and Mars offer valuable lessons for understanding planetary habitability. Venus shows how a planet with the right initial conditions can spiral into uninhabitability if its climate system becomes unbalanced. Mars, on the other hand, demonstrates how vulnerability to atmospheric loss and cooling can stifle potential habitability. These insights are particularly relevant for the study of exoplanets. By examining the factors that shaped Venus and Mars, scientists can refine their models for identifying potentially habitable worlds in other solar systems. For instance, a planet's size, atmosphere, geological activity, and position within its star's habitable zone are all critical factors to consider. Mars and Venus have different paths in their stories. Mars was frigid and lonely because it couldn't retain its atmosphere, while Venus became a blazing wasteland due to its runaway greenhouse effect. Their interconnectedness emphasizes the precarious equilibrium necessary for the emergence and survival of life. The search for extant life on Mars. The discovery of extant life on Mars would be one of humanity's most profound scientific achievements. It would suggest that life is not an Earth-exclusive phenomenon, but rather a cosmic inevitability under the right conditions. Such a discovery would bolster the theory that Mars was habitable billions of years ago and might have even seeded life on Earth through panspermia. Extant life would also reshape astrobiology, demonstrating how organisms can adapt to environments that challenge every assumption we have about the requirements for life. On a practical level, finding life today on Mars would provide a unique opportunity to study a second independent genesis of life, if it indeed arose separately from Earth's life forms. Even if Mars's microbes share genetic similarities with Earth organisms, such as DNA or RNA, it could support the theory that life traveled between planets in our solar system. Either scenario would profoundly expand our understanding of life's origins and adaptability. The search for life on Mars has gained momentum, thanks to advanced robotic missions meticulously designed for astrobiological exploration. NASA's Perseverance rover, currently exploring Jezero crater, represents one of humanity's most ambitious attempts to unravel Mars's mysteries. This ancient river delta, believed to have harbored water billions of years ago, is an ideal location to hunt for biosignatures, molecular or morphological evidence of life. Perseverance's suite of instruments, including Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, is finely tuned to detect organic molecules and identify potential microfossils embedded in Martian rocks. The European Space Agency and Roscosmos's Rosalind Franklin rover, slated for a future launch, adds another layer of promise. Equipped with a 2-meter drill, it can access subsurface regions that are better shielded from Mars's harsh radiation, a critical factor since surface conditions might have obliterated any organic evidence. By probing beneath the Martian crust, Rosalind Franklin aims to find preserved organics and analyze their chemical composition using its Mars Organic Molecule Analyzer, MOMA. NASA's Curiosity rover continues to play a vital role in this search, despite its focus on ancient habitability rather than extant life. By analyzing samples from Gale Crater, Curiosity provides invaluable data on Mars's past environments and helps refine the search for potential habitats where life could still persist. Detecting life is no small feat, especially on a planet as barren and hostile as modern Mars. To overcome these challenges, scientists have developed sophisticated techniques to identify biosignatures, signs that life is or was present. One of the most promising methods involves subsurface drilling. The surface of Mars is bombarded with radiation from the Sun, breaking down organic molecules over time. Subsurface environments, shielded by layers of rock and soil, offer a refuge where biosignatures might remain intact. Spectroscopy tools aboard rovers, like Perseverance's Raman and fluorescent spectroscopy instruments, analyze the molecular composition of Martian samples. These devices can identify carbon-based compounds, the building blocks of life, and differentiate between those formed by biological or non-biological processes. Analysis of the atmosphere is another important method. Mars's atmospheric methane levels change with the seasons, which may be an indication of microbial activity. The purpose of instruments such as the Trace Gas Orbiter is to identify the origins of methane and determine if it is produced by living things or by geological processes. You can tell if these gases have biological or abiotic sources based on the isotopic ratios of components like carbon and oxygen. Where might life persist on Mars today? The most likely refuges for extant Martian life are environments that provide stable conditions and access to liquid water, albeit in limited or transient forms. One such habitat is subsurface brines, salty reservoirs of liquid water that can remain in a liquid state despite Mars's freezing temperatures. Radar studies suggest the presence of such briny lakes beneath the planet's south polar ice cap, making these areas prime candidates for future exploration. Another potential habitat is Mars's polar ice caps, which could harbor ancient microbial life preserved in the frozen layers. Seasonal melting at the edges of these ice caps might create short-lived liquid environments where microorganisms could survive. Caves and lava tubes offer another intriguing possibility. These natural structures are insulated from the surface's extreme temperature swings and radiation, creating more stable microclimates. If water ice or brine accumulates within these caves, they could provide a sanctuary for microbial communities. Recurring slope lineae, RSL, dark streaks that appear on Martian slopes during warm seasons, might indicate the flow of briny water. Although their exact nature remains debated, RSL sites are of great interest for robotic exploration. The quest for extant life on Mars will rely heavily on future missions designed to explore regions that current rovers cannot reach. The Mars Sample Return (MSR) mission, a collaboration between NASA and the European Space Agency, aims to retrieve samples collected by Perseverance and return them to Earth for detailed laboratory analysis. These samples could contain preserved organic compounds or even microbial life, offering conclusive evidence that life exists or existed on Mars. Human exploration of Mars, a goal championed by NASA and private companies like SpaceX, holds the potential to accelerate this search. Astronauts would have the capability to explore diverse terrains, drill deeper than robotic probes, and conduct in situ experiments with greater flexibility. Additionally, they could access promising sites, like caves or polar regions, that are currently out of reach for robotic missions. Technological advancements will also enhance the search for life. Proposed missions, such as the Mars Ice Mapper, aim to locate subsurface ice deposits that could serve as habitats. Future orbiters with high-resolution imaging and spectroscopic capabilities will refine our understanding of Mars's most promising regions. The search for extant life on Mars goes beyond scientific curiosity. It has profound implications for humanity's future. On a practical level, finding life would validate Mars as a potential site for future colonization, where humans could harness resources like water to sustain long-term settlements. It also raises ethical questions about planetary protection. How do we ensure that Earth life does not contaminate Mars, and vice versa? On a broader scale, the discovery of life on Mars would redefine humanity's place in the universe. It would suggest that life is not unique to Earth, but rather a common outcome of planetary evolution, reshaping our understanding of biology, evolution, and the conditions that make a world habitable. Mars and Earth, divergent paths. From the very beginning, Mars was at a disadvantage. Its smaller size meant weaker gravity, making it more difficult to hold on to an atmosphere. Over time, this vulnerability would prove critical. As solar winds bombarded the planet, the lighter elements of its atmosphere, like hydrogen and helium, escaped into space. With each passing eon, Mars became increasingly barren. Earth, with its greater mass, was able to retain its atmospheric integrity, preserving the essential gases that sustain life. Smaller planets like Mars also cool much faster than their larger counterparts. While Earth's molten core continues to churn, driving volcanic activity and maintaining its magnetic field, Mars cooled rapidly. This early cooling led to the solidification of its core, extinguishing the dynamo effect that generates a magnetic field. Without this protective shield, Mars's atmosphere became even more vulnerable to the Sun's relentless winds. Mars's once thick atmosphere was a key player in its ancient habitability. Billions of years ago, it was dense enough to support rivers, lakes, and even potential oceans. But as its magnetic field faded, the solar wind began stripping away the atmosphere. This process, captured vividly by instruments aboard the MAVEN spacecraft, left Mars with a thin veil of carbon dioxide, barely sufficient to trap heat or sustain liquid water on the surface. Earth, in contrast, has retained a robust atmosphere. Its magnetic field, generated by the continuous motion of its liquid outer core, deflects harmful solar winds. This shield not only preserves Earth's atmosphere, but also allows for a stable climate that has fostered life for billions of years. Beneath Earth's surface, tectonic plates shift and collide, shaping continents, creating mountains, and recycling carbon dioxide. This dynamic system plays a crucial role in regulating the planet's climate through the carbon cycle. Volcanic eruptions release carbon dioxide into the atmosphere, while subduction zones draw it back into the mantle. This balance has been instrumental in preventing runaway greenhouse effects or severe cooling events. Mars, however, lacks this vital process. With no active plate tectonics, its surface has remained largely static. Features like Olympus Mons, the tallest volcano in the solar system, testify to a planet where volcanic activity was once intense but has long since subsided. The absence of tectonics on Mars not only stunted its geological evolution, but also left it unable to recycle key elements needed to sustain a stable atmosphere and climate. Earth's magnetic field does more than deflect solar winds. It also plays a role in protecting the biosphere. By shielding the planet from harmful radiation, the magnetic field creates a stable environment for life to evolve. Mars, after losing its magnetic field, was left exposed to intense radiation, making its surface a hostile environment. Any potential life on Mars would have been forced underground or into transient habitats where protection was available. Mars and Earth share a watery past. Ancient Mars was home to flowing rivers, expansive lakes, and possibly even oceans. Evidence from the Curiosity and Perseverance rovers, as well as orbiters like Mars Reconnaissance Orbiter, reveals clear signs of water-carved valleys and sedimentary formations. Yet Mars's water slowly escaped into space or became trapped as ice beneath its surface. The water cycle has remained active, driven by the interplay of atmospheric pressure, gravity, and temperature. Rain falls, rivers flow, and oceans churn, a continuous cycle that not only sustains life, but also shapes the planet's surface. Mars's lack of sufficient gravity and atmospheric pressure rendered it incapable of sustaining such a cycle, leaving behind dry riverbeds and frozen polar caps as relics of a wetter past. In its youth, Mars was geologically alive. Volcanoes like Olympus Mons and Tharsis Montes erupted with ferocity, reshaping the landscape and pumping gases into the atmosphere. These volcanic activities may have played a critical role in creating a greenhouse effect, warming the planet enough to sustain liquid water. However, as Mars's interior cooled and its volcanic activity ceased, the planet lost this vital source of atmospheric replenishment. Earth, with its larger size and slower cooling rate, continues to experience volcanic activity. This ongoing geological vitality not only contributes to the atmosphere, but also creates diverse habitats, from hydrothermal vents to fertile volcanic soils where life can thrive. The carbon cycle controls the Earth's greenhouse effect, which maintains a mild climate. In contrast, Mars went through a greenhouse collapse. Its thermal capacity decreased as its atmosphere dwindled. As a result of the precipitous drop in surface temperature, the last of Mars' water vapor solidified into the icy desert that we observe today. This striking difference highlights the fine equilibrium needed to keep a place habitable. The Sun's energy is a double-edged sword. Mars, being farther from the Sun, receives less solar energy, contributing to its colder climate. Earth, positioned in the Sun's habitable zone, benefits from just the right amount of energy to sustain liquid water and a stable climate. However, Mars's distance may have initially shielded it from the runaway greenhouse effect that doomed Venus, allowing it a brief window of habitability. Asteroids and comets pounded Mars and Earth throughout the late heavy bombardment. These impacts not only supplied organic materials and water, but they also devastated large areas. Earth was able to heal and reconstruct because to its thicker atmosphere and increased tectonic activity. Because of its thin atmosphere and geologically static surface, Mars had a hard time getting back on its feet, which further limited its capacity for development. Imagine if Mars had been just a bit larger or closer to the Sun. With a stronger gravitational pull and a more robust magnetic field, it might have retained its atmosphere and water, potentially evolving into a lush, habitable world. The divergent paths of Mars and Earth provide invaluable lessons about the delicate interplay of size, distance, geology, and atmospheric dynamics in shaping planetary habitability. Could Mars have seeded Earth? Mars and Earth share a unique cosmic relationship, orbiting the same Sun, yet following vastly different paths of evolution. Among the many theories that speculate on the origin of life, one of the most compelling asks whether Mars could have played a pivotal role in life's emergence, not just for itself, but for Earth as well. This theory, often linked to the idea of Panspermia, suggests that Mars, with its earlier habitable conditions, may have been the cradle of life, seeding Earth during the chaotic early years of the solar system. Imagine a young solar system, chaotic and violent, filled with asteroid collisions and planet-shaping impacts. This early solar system wasn't a static place. Material regularly traveled between planets. Mars, with its lower gravity and thinner atmosphere, was uniquely positioned to eject fragments of its crust into space during these intense bombardments. These fragments, propelled by massive impacts, could escape Mars's gravity more easily than material leaving Earth, making it plausible for rocks carrying Martian microbes to travel across the void and land on our planet. Studies of Martian meteorites discovered on Earth provide a tantalizing glimpse into this interplanetary exchange. These rocks, including the famous ALH 84001 meteorite, hold chemical fingerprints that confirm their Martian origin. The existence of these meteorites proves that material from Mars has made its way to Earth. Could these rocks have carried something more, microscopic life, protected within the rocky shield of Martian debris? For life to journey from Mars to Earth, it must endure the extremes of space, intense radiation, freezing temperatures, and the vacuum of the cosmos. Remarkably, research on extremophiles, organisms that thrive in Earth's harshest environments, shows that some life forms might indeed be capable of surviving such conditions. Microbes like Deinococcus radiodurans can withstand high doses of radiation, while tardigrades, microscopic water bears, can enter a state of cryptobiosis, surviving for decades without water or air. These resilient creatures offer compelling models for how Martian life could endure a journey to Earth. Laboratory experiments have further supported this idea. Simulations of impact shocks, space vacuum, and atmospheric entry suggest that microbial life embedded within rock fragments could survive the violent ejection from Mars, the cold and radiation of space, and the fiery descent through Earth's atmosphere. These findings reinforce the plausibility of panspermia, demonstrating how life could make an interplanetary leap. Martian meteorites like ALH 84001 aren't just geological anomalies, they're time capsules from a planet that once had conditions favorable for life. This meteorite, discovered in Antarctica in 1984, sparked intense debate when researchers identified structures resembling microfossils and magnetite crystals that some argued were biological in origin. Though the biological interpretation remains controversial, the discovery underscored the potential for Martian rocks to carry evidence of ancient life. Scientists have also found organic molecules within some Martian meteorites. While these molecules don't prove the existence of life, they hint at the chemical processes that might have been occurring on early Mars. The isotopic composition of carbon within these meteorites suggests that Mars was a chemically active world billions of years ago, potentially capable of supporting life. These findings add weight to the idea that life, or at least its building blocks, could have existed on Mars before Earth. Mars, a head start in the race for life. To understand why life might have started on Mars before Earth, we need to examine the two planets' early histories. Mars, being smaller than Earth, cooled more quickly after its formation. This rapid cooling allowed Mars to develop a stable crust and liquid water on its surface much earlier than Earth, which was still a molten, inhospitable world during this time. Ancient Mars had rivers, lakes, and perhaps even oceans, environments ripe for the emergence of microbial life. Mars's early climate was also more favorable for habitability. Geological evidence suggests that it had a thicker atmosphere billions of years ago, providing protection from radiation and helping to maintain liquid water on the surface. Combined with volcanic activity and a magnetic field that shielded the planet from solar winds, early Mars might have been a more stable and hospitable environment for life than Earth at the same time. The journey of Martian material to Earth wasn't a rare event. During the solar system's late heavy bombardment period, a time of intense asteroid and comet impacts, material was frequently exchanged between planets. Astrophysical models estimate that billions of tons of Martian rock could have landed on Earth over time. Given these numbers, it's not far-fetched to imagine that some of these rocks carried microbial passengers. While the idea of Mars seeding Earth is intriguing, It's important to consider the counter-arguments. Earth, with its larger size and more stable conditions over time, is also a strong candidate for the origin of life. Deep-sea hydrothermal vents on Earth provide a compelling model for abiogenesis, the natural process by which life arises from non-living matter. These vents, rich in heat and minerals, could have acted as cradles for the first microbes. In addition, Mars lost its magnetic field early in its history, while Earth's atmosphere has provided stronger long-term shielding from radiation. Much of Mars's atmosphere and liquid water was stripped away when this loss exposed the surface to the severe solar winds. As Mars grew more uninhabitable, any life that did emerge there would have had a tough time surviving. Some scientists argue that Earth's robust and diverse biosphere indicates an independent origin of life. They suggest that Earth's abundant water, dynamic plate tectonics, and protective atmosphere provided all the necessary ingredients for life to emerge and flourish without external influence. NASA's Perseverance rover, currently exploring Jezero crater, is searching for signs of ancient microbial life. This crater, an ancient lakebed, is a prime location for preserving biosignatures. Perseverance is also collecting rock samples that future missions will return to Earth for detailed analysis. These samples could reveal whether Mars once harbored life and whether it shares a common ancestry with life on Earth. The upcoming Mars Sample Return mission, a collaboration between NASA and the European Space Agency, will be a critical step in answering these questions. By bringing pristine Martian samples back to Earth, scientists can analyze their chemical and isotopic composition with unparalleled precision. If these samples contain evidence of past life, it could reshape our understanding of life's origins in the solar system. What would Martian life mean? The discovery of life on Mars would mark a watershed moment in our understanding of the universe. Life on Earth has always been considered exceptional, a unique occurrence in an otherwise vast and lifeless expanse. But evidence of life on Mars, past or present, would shift that narrative dramatically. It would suggest that life may not be a rare phenomenon, but a natural result of certain environmental conditions. This would challenge the Copernican principle once more, reinforcing that Earth is not the center of the biological universe. If Earth life originated on Mars through interplanetary seeding, a concept known as Panspermia, it would revolutionize our understanding of biological lineage. Earth's status as the singular cradle of life in the solar system would give way to Mars, painting the red planet as the elder sibling in the story of life. Alternatively, finding independent life on Mars would suggest that life could arise in multiple places independently, making the galaxy seem infinitely more hospitable to life than we once believed. The ethical implications of discovering Martian life are staggering. If life exists on Mars today, even in microbial form, humanity must grapple with the morality of further exploration. Would it be ethical to send humans to Mars, potentially contaminating its ecosystem? This raises profound questions about our responsibility as stewards of the cosmos. Do we have the right to interfere with alien life, even if it is microscopic? Should Mars, like certain parts of Earth, be declared a protected environment, free from human exploitation? These considerations extend to legal frameworks. International agreements such as the Outer Space Treaty emphasize the importance of preventing biological contamination, but they were drafted before the serious possibility of finding life on Mars became apparent. If life is discovered, new treaties may be necessary to ensure that humanity balances exploration with preservation. Some argue that Martian microbes, if they exist, should have intrinsic rights, preventing humans from exploiting or interfering with their habitat. Mars's history could hold lessons for Earth's future. If Mars once had thriving life that later went extinct, it becomes a cautionary tale of planetary fragility. What led to its decline? Was it the loss of its magnetic field and subsequent atmospheric stripping? Or was it something more catastrophic? Understanding these factors could inform efforts to prevent similar outcomes on Earth. On the other hand, Mars could represent a backup plan for humanity. If life is not found on Mars, it clears the way for terraforming efforts, which could one day transform the red planet into a habitable world. But if life exists, the justification for colonizing Mars becomes murkier. Could humans coexist with Martian life, or would our presence inevitably disrupt it? These questions force us to consider whether humanity's survival outweighs the preservation of an alien biosphere. Discovering life on Mars would also ripple through spiritual and religious communities worldwide. Many religious narratives are deeply tied to Earth's uniqueness as the home of life. Evidence of life on Mars might challenge these narratives, forcing reinterpretations of sacred texts and beliefs. For some, it could reinforce a sense of divine wonder, that life exists not just on Earth, but across the universe. For others, it could prompt a re-examination of humanity's role in the cosmos, perhaps even diminishing Earth-centric spiritual views. Conversely, the discovery could unify humanity. Realizing that life exists beyond Earth might inspire a collective sense of awe and humility. Fostering a global perspective, it could remind us that we are all part of a shared journey in a vast, interconnected universe. In this way, Martian life might become a unifying force, bridging divides and inspiring a sense of common purpose. The discovery of life on Mars would signal a new chapter in human history. It would mark the moment humanity transitioned from an Earthbound species to one capable of exploring and potentially interacting with alien biospheres. This transition would redefine human identity. We would no longer be solely Earthlings. We would become interplanetary beings with responsibilities and opportunities that extend far beyond our home planet. Mars would inspire a new wave of literature, art, and philosophy. Just as the moon landings in 1969 inspired a generation, the discovery of life on Mars could spark a renaissance of creativity and innovation. It could lead to new ways of thinking about coexistence, not just with other humans, but with entirely alien life forms. Mars's history has the potential to alter Earth's as well. Human and biological history would be rewritten if life on Mars first emerged and then made its way to Earth. It would show that life can persist in the face of adversity, highlighting the interdependence of all worlds. The discovery of life on Mars would redefine the search for life elsewhere. If life arose on both Earth and Mars, it would suggest that the conditions for life are not as unique as we once thought. This would shift the focus of exploration to other solar system bodies, such as Europa, Enceladus, and Titan, and even to exoplanets orbiting distant stars. Mars would serve as a stepping stone, providing a blueprint for identifying life in other extreme environments. Technologically, Mars discoveries could accelerate advancements in space exploration. From improved drilling techniques for subsurface biosignatures to advanced life detection instruments, the tools developed for Mars could be adapted for use on other worlds. These innovations would bring us closer to answering one of humanity's oldest questions. Are we alone? If Mars once supported life, it would reinforce the idea that life is resilient and adaptable. It thrives in conditions we might consider inhospitable, from the acidic waters of Earth's volcanic springs to the icy subsurface oceans of Jupiter's moons. Mars would serve as a testament to life's tenacity, expanding our understanding of what is possible in the universe. A number of issues about planetary connectivity have been brought up by Mars's narrative. Are Mars and Earth really two distinct worlds, or are they rather nodes in a common biological network, assuming life does, or did, exist on both of these planets? This theory posits that the planets are not completely separate from one another, but rather that they are all involved in complex cosmic webs. The potential extinction of Martian life also serves as a sobering reminder of life's fragility. It underscores the delicate balance required to sustain a biosphere and highlights the importance of preserving Earth's environment. Mars's history could become a symbol of what happens when a planet loses its ability to support life. The discovery of life on Mars would leave an indelible mark on future generations, It would inspire long-term investments in science, education, and space exploration, laying the groundwork for humanity's next great leap. Mars would become a symbol of what humanity can achieve when it works together, fostering a sense of global unity. But Mars's legacy would go beyond inspiration. It would challenge humanity to think critically about its role in the cosmos. Are we stewards of life, responsible for its preservation, or explorers with an inherent right to push boundaries? These questions will shape the future of space exploration and define humanity's relationship with the universe. Perhaps the most profound question Mars poses is, who are we? If life originated on Mars and spread to Earth, it would mean that we are, in a sense, Martians. This realization would challenge our identity as Earthlings and force us to consider our place in the broader cosmic tapestry. What does it mean to be human if our origins lie on another world? Mars also makes one wonder why we're here. Does the very fact that we exist depend on chance and fate? Or is it a universal occurrence that follows the rules of the cosmos and cannot be prevented? Mars could help us get closer to the answers to these issues that have plagued humanity for thousands of years. Mars's history may even provide light on the so-called Great Filter, a theoretical barrier that explains our lack of contact with advanced alien cultures. If all life on Mars were to suddenly end because of a catastrophic environmental breakdown, it may show us how difficult it is for any kind of life to stay alive. At its core, Mars is a philosophical benchmark rather than merely a scientific one. Its narrative goes beyond facts and theories to provide a prism through which people may consider their place in the universe, their own identity, and what the future holds. Future exploration and discoveries. Mars as a beacon of human curiosity. The journey to uncover Mars's secrets is far from over, and upcoming missions are poised to take our understanding to new heights. Among these, NASA and the European Space Agency's ESA Mars Sample Return mission stands out as a groundbreaking endeavor. This multi-phase project involves collecting and transporting Martian soil and rock samples back to Earth for in-depth analysis. These samples, currently cached by the Perseverance rover, will be retrieved and delivered by an ambitious collaboration of landers, ascent vehicles, and orbital transfer systems. On Earth, they'll undergo scrutiny with instruments far too large or complex to send to Mars, potentially revealing traces of ancient microbial life or confirming the presence of organic molecules with unprecedented precision. The Rosalind Franklin rover, a flagship mission under the ExoMars program, is another key player. Named after the scientist who contributed to the discovery of DNA structure, this rover is uniquely equipped to drill up to 2 meters below the Martian surface. This capability is critical since the surface is bombarded with radiation, making it inhospitable to life as we know it. By exploring subsurface regions, the rover may uncover well-preserved biosignatures in ancient sediments. China is also advancing its Martian exploration goals. Following the success of the Tianwen-1 orbiter and Zhurong rover, the proposed Tianwen-3 mission aims to return Martian samples to Earth by the late 2020s, complementing Western efforts and ensuring a global approach to the Red Planet's mysteries. Meanwhile, next-generation orbiters like the Mars Ice Mapper will focus on surveying subsurface ice reservoirs. Understanding these reserves is crucial not just for scientific knowledge, but for the practicalities of future human missions. Such discoveries could revolutionize our understanding of water cycles on Mars and serve as essential resources for sustained human presence. Private companies, too, are making strides. SpaceX, with its bold vision of colonizing Mars, is developing reusable spacecraft capable of transporting humans and cargo. While its primary goal is to establish a self-sustaining Martian colony, the infrastructure it creates could provide unparalleled opportunities for scientific exploration. The field of astrobiology has seen remarkable advancements, many of which are directly applicable to Mars exploration. Biosignature detection remains a top priority, with cutting-edge instruments designed to identify isotopic patterns or molecular structures indicative of biological processes. For example, next-generation spectrometers can detect subtle variations in carbon or methane isotopes that might suggest biological origins. Mars's water cycle is another focus of study. While liquid water doesn't exist on the surface today, recent findings suggest transient briny flows may occur under specific conditions. These discoveries challenge traditional views of habitability, extending the range of environments where life might persist. On Earth, scientists are refining their techniques in Mars analog environments, such as Antarctica, the Atacama Desert, and the dry valleys of the Arctic. These harsh landscapes mimic Martian conditions, providing a testing ground for instruments and strategies. Meteorites from Mars, found on Earth, continue to be valuable resources. Each contains a snapshot of Mars's past, revealing details about its volcanic activity, atmosphere, and potential for life. Combined with data from orbiters and rovers, these meteorites provide a more complete picture of Mars's history. Robotic missions, as advanced as they are, have limitations. Human exploration could transform Mars science by introducing adaptability, intuition, and the ability to make real-time decisions. Astronauts could explore regions inaccessible to rovers, rapidly adjust plans based on observations, and conduct experiments on site. The capacity to go further into the Martian subsurface is one of the greatest benefits of human exploration. Human crews using sophisticated equipment might reach strata tens of meters deep, where remnants of ancient life may be preserved. But rovers like Rosalind Franklin can only drill a few meters. Additionally, humans could deploy and operate advanced laboratory equipment on Mars itself, reducing the risks of contamination associated with transporting samples back to Earth. This capability would enable the analysis of sensitive materials without the delays of interplanetary travel. Future human missions may also investigate terraforming concepts on a small scale, creating localized habitable zones to support long-term exploration. These experiments could lay the groundwork for making Mars more accommodating for life, both human and microbial. Mars's proximity and relative accessibility make it an ideal training ground for venturing deeper into the solar system. The lessons learned from Mars exploration about surviving in harsh conditions, resource utilization, and dealing with isolation will be invaluable for missions to icy moons like Europa and Enceladus, which may harbor subsurface oceans beneath their frozen crusts. Moreover, Mars's lower gravity makes it an excellent launch platform for missions to the asteroid belt or beyond. Its position in the solar system provides strategic advantages for exploring other celestial bodies. Human settlements on Mars could serve as forward bases for deep space observatories. Freed from Earth's atmospheric distortions, telescopes on Mars could offer clearer views of distant exoplanets and other galaxies, advancing our understanding of the universe. Mars has long been a symbol of humanity's aspirations. From ancient mythology to modern science fiction, the Red Planet has inspired countless stories, ideas, and innovations. Today, it serves as a unifying goal for nations, fostering international collaboration in science and technology. The pursuit of Mars exploration also fuels public interest in STEM fields, inspiring future generations of scientists, engineers, and thinkers. Each mission captures the imagination, showing what humanity can achieve when driven by curiosity and determination. Exploring Mars also provides a stark reminder of our planet's fragility. Mars, with its desolate landscapes and once vibrant history, shows us the importance of protecting Earth's ecosystems. Understanding what went wrong on Mars could help us avoid similar fates on our home planet. Throughout human history, the quest to understand where we come from has been as much about looking outward as inward. Among all celestial bodies, Mars has emerged as a focal point of this search, tantalizing us with its secrets and possibilities. Could life have started there, on the Red Planet, and somehow found its way to Earth? Or might the ancient rivers and lakes of Mars tell a parallel story of a world that could have been, had circumstances aligned just a little differently? As we draw to the end of this exploration, let's reflect on the profound implications of our ongoing investigation into the Red Planet. Mars, long a symbol of mystery and exploration, has consistently drawn humanity's attention, not just for its proximity, but for its striking similarities to and differences from Earth. It was once a world of rivers, lakes, and even oceans, holding the key ingredients for life as we know it. From studying its lost atmosphere to analyzing the mineral-rich terrain and its long-dormant volcanic activity, Mars offers an invaluable lens into the potential origins of life in our solar system. Theories such as Panspermia and the interplanetary exchange of meteorites challenge the idea of Earth as an isolated cradle of life. These theories propose that Mars, with its earlier habitability window, could have seeded Earth with microbial life or vice versa. The discovery of organic molecules, the evidence of ancient water, and even the detection of methane fluctuations suggest a planet that was once alive in ways we are only beginning to understand. What if the first microbial life forms arose not on Earth but on Mars? The idea, though staggering, is not implausible. Mars's environment billions of years ago was arguably more hospitable than Earth's, with liquid water flowing across its surface, a thicker atmosphere, and a magnetic field shielding it from harmful solar radiation. Life could have arisen in its lakes or hydrothermal vents, evolving before Earth's chaotic environment settled into stability. If such life existed, could it have traveled to Earth? Meteorites from Mars have been discovered on our planet, their journeys propelled by powerful cosmic impacts that ejected chunks of Martian rock into space. These meteorites contain tantalizing hints, traces of organic compounds and microstructures resembling fossils, though their interpretation remains contentious. If life truly hitched a ride from Mars to Earth, it would mean that we, as a species, owe our existence to a planet now defined by its barrenness. Whether life began on Mars or not, the Red Planet remains a critical piece of the puzzle in understanding life's potential in the universe. Its history of water activity, its geological diversity, and even its atmosphere, thin and depleted as it is, provide a comparative framework against which we can measure Earth's extraordinary capacity to support life. Mars reminds us that habitability is not just about water or even the right chemical ingredients, but about the delicate balance of planetary conditions. The story of life's origins is far from complete, but each new discovery on Mars brings us closer to answering the ultimate question: are we alone, or are we part of a cosmic family, connected by the threads of life that began far beyond our home? As we continue exploring the Red Planet and pushing the boundaries of science, the answers we seek may redefine our place in the universe. Thank you for joining us on this journey through time and space. If you're as fascinated by the mysteries of life and the cosmos as we are, don't forget to like, share, and subscribe. Hit that notification bell so you don't miss out on our next adventure into the unknown. Until then, keep wondering, keep exploring, and remember, our story is written in the stars.